So here we've got the logism of all the different um, memory gates that we looked at. We've got the D, T, the SR, and the JK. All of them are synchronous, so we have the clock plugged into all of them. As they also have the asynchronous control. Up here we have the set, which turns all of them to 1, and the reset, which automatically turns them all to 0. The purpose of those is if you need a control that changes what the value is outputting without having to wait on the clock, all the other controls will be synchronous, which essentially means that they'll only trigger once every clock cycle. Also, we can see that it's positively edged, which means that as the clock ticks, only on the negative to positive edge will the memory change. Um, so, so there's two strokes. There's the downstroke and the upstroke. The upstroke from 0 to 1 is when our gates will update. So first we have our D gate here. This one's the simplest, I'd say, out of all of them. All it does is take the D value and update the output to that value every clock cycle. So since it's 1 right now, the clock is cycled and we see that it's 1. And when we turn it to 0, as soon as the clock goes cycles, it turns back to 0. We can pause the clock to get a better look at it. So we'll turn clock to off and then this to 1, and as soon as this goes up, it's on. Clock goes back down, back up, and it stays 1. And then when it's off and we turn it on, we can see it updates to 0. If we turn it on now, when it goes down, nothing will happen. It's a positive edge. If we wanted a negative edge, we would just knot the clock value as it goes into the gate. When we go back up, it updates to 1. So that's the D gate. The T gate is similar. We'll get the clock running again. T is similar. Since there's only one input, but with this one, a 1 value into the T input will tell the gate to toggle every clock stroke. So if it's 1 and the clock strikes, then the output of Q will change to the opposite of whatever its previous value is, or whatever the value is right now, it'll become the opposite. So right now it's off, and 0 for T is no change, which means Q will stay constant. So we can turn it on. As we see, every time the clock goes up, the value changes. And then when we turn it off, whatever value it's on will stay. This is one of the easier gates to see exactly what it's doing. Since it's off, nothing happens, and when it's on, we can see it change with every clock cycle. We can turn it off to get a better look at it. Turn off the clock. So it's 1, clock goes up, changes to 0, down, and back up for the next cycle. It goes back to 1. And then when it's T is 0, the clock does nothing. Next we'll look at the SR. So the SR actually has 2 inputs, which gives us 4 different outputs. There's 4 different combinations we can make between the two of these. The first one we'll look at is 0, 0. As we can see, that's where it's at right now, and nothing's happening. And that's because this is no change mode. Whatever the value of Q is will stay the same when the clock cycles, as long as S and R are both set to 0. The next mode we have is when R is set to 1 and S is 0. This will output a 0 no matter what. If the last input or the last Q value is a 0 like it was, and we have R turned on and S turned off, so 0, 1, then we can see the Q output's a 0. If it were a 1, when the clock cycles, it would become a 0. And to get a 1, it's the opposite of that. It's 1, 0. So the S value is the 1 and the R is the 0, which gives us our third possible combination. And then we can show that when we go back to 0, 0, there's no change. And then when we go to just R, it changes back to 0. We can turn it off, no change. And that's pretty much all this gate does. And like I said, there's 4 combinations we can make, but the 1, 1 doesn't actually have any function at this gate. Its only purposes are to turn it on, no change, and to turn it off. As we can see, it's moving with the clock cycle on the positive edge, just like the other gates were. And also something on all these gates that I didn't mention, they have 2 outputs, only one of which is being used. The other one is just the knotted output, because in the lower level circuits that build these up, we actually get 2 outputs just from the way they're structured. So these gates give us both in case you want the opposite, but we won't use those right now. Okay, so next we have the JK, which is the last, and I like to think of it as a mix between the toggle and the SR, because the functions are essentially as all the same functions as the SR. There's no change right now. K1 and J0 gives us Q0, J1 and K0 gives us 1, and 0, 0, no change again. But then it also has a function for both J and K set to 1, which is to toggle. Every upstroke we can see that it toggles. And then if we wanted to, well, let's stop the clock real quick. If we wanted to stay from a toggle, we would turn both of them off, and then whatever it's set to will stay constant with the no change mode. And then the K value, we can turn it to 1, and we see we get it to change to 0. J will turn it back on, both of them toggle. So those are all the functions or those are all the memory gates and their functions. They all use sequential circuits inside of them, which allow us to use past or feedback loops to store memory essentially. And I think that's pretty much it. We still have the set and the reset, which turn on and off our gates asynchronously. So there's different ways we could implement that to other applications in the real world, other circuits we might want to make. But yeah, I think that's it. Thank you, and bye.